This Scalativity episode discusses why I believe our solar system was a cosmic scale neutron and is now cosmic scale beta decaying. Astronomers explain stars form from initially dispersed gaseous dust clouds that contract and continue to rise in temperature until deep in their interior fusion ignites. In fractal physics, the star is already formed as a compact solid, cold and dark. Its liquid helium ocean, the universe's thermonuclear engine coolant, boils away because insufficient positive charge is present to prevent cosmic rays from striking the surface, transmuting hydrogen into a buildup of deuterium and tritium until fusion ignites. But how can a neutron look like a very tiny star with even tinier planets orbiting it? This amazing wonder to the quantum scale remains hidden to the human scale for two main reasons. First, the rate of time passage depends on relative scale. Einstein explained the rate of time passage depends on the relative velocity between two reference frames. In fractal physics, the rate of time passage also depends on the relative size difference between two reference frames. Second, the elusive neutrino is incoherent, spherically radiated subquantum scale photons. Subquantum scale photons are not known in modern physics. They are similar to photons. They travel at the speed of light. They have wavelengths and frequencies. However, their energy packets are far too minute to currently be detectable. If the human scale could video record neutrino energy with femtosecond frames during the entire microsecond that a neutron decays into a proton and an electron, then stretch out this video to about 10 minutes, we could view 12 billion years of the Lilliputian scale in 12-year increments, starting with a quantum scale cold dark star beginning its subquantum scale fusion, transforming into a quantum scale hot bright star, overheating and swelling out into a large disk to cool, depositing Lilliputian scale heavy metals at various radii while contracting. The central quantum scale star settling into a steady state of subquantum scale hydrogen fusing into subquantum scale helium, while quantum scale planets form in their orbits. The quantum scale star shining and the quantum scale planets orbiting for several minutes. Then all the subquantum scale iron and subquantum scale nickel of the quantum scale planets forming into a single electron, a quantum scale supernova explosion launching a glowing hot electron in one direction and a glowing hot proton recoiling in the opposite direction. Both the proton and the electron quickly cooling to complete darkness, invisible even to our quantum camera video recorder. Imagine the excitement from discoveries made by quantum scale cameras video recording inside radioactive materials, watching entire galaxies form, grow, merge, then fade, finding the true lifetimes of quasars and pulsars, observing all types of supernova explosions, as many as you want, discovering if we can observe the moment of alpha decay or of fission-scission, witnessing gamma ray bursts from neutron collisions, placing the entire universe under the fractal microscope. Will someone out there please build us a quantum scale camera to image neutrino energy? Why do I believe? our solar system was a cosmic scale neutron and is now cosmic scale beta decaying? First, if our universe is 1.5 milliseconds into a 500 megaton fission explosion relative to the Titanic scale, then many cosmic scale neutrons exist, traveling in all directions at various speeds, some of which will be undergoing the process of cosmic scale beta decay. Second, of all cosmic scale objects, only starlight, including the final supernova outburst, would appear self-similar to a neutrino when viewed from the Titanic scale. The luminous output of a star, its sum of electromagnetic radiation and neutrino radiation, is practically self-similar to one cosmic scale antineutrino. Third, iron, nickel, and cobalt are all stable thermonuclear endpoints. Fusion of lighter elements stop releasing energy at iron, nickel, and cobalt. When cool enough, iron, nickel, and cobalt are all ferromagnetic. A negatively charged, planet-sized, magnetized cannonball is a good candidate for a cosmic scale electron. Fourth, the neutron decays into two particles, a proton and an electron, while emitting neutrino energy. The mass of the neutron divided by 1839 equals the mass of the electron. The mass of the Sun divided by 1839 should equal the mass of a cosmic scale electron, 1 times 10 to the 27 kilograms. The mass of Jupiter is 2 times 10 to the 27 kilograms, while the 8 planets total 3 times 10 to the 27 kilograms. Is this just a coincidence? Maybe. Fifth, when a neutron decays, the energies of the proton, the electron, and the antineutrino all vary. However, the total decay energy remains the same, 0.8 million electron volts. The same factor, 1 times 10 to the 57, used to scale a mass from the quantum scale to the cosmic scale, is used to scale an energy from the quantum scale to the cosmic scale. 0.8 million electron volts scales up to 1.5 times 10 to the 44 joules. The Sun's luminosity radiates an energy equal to 1.1 times 10 to the 44 joules in 9 billion years. The Sun radiates a total energy close to a cosmic scale neutron's total decay energy. Is this just a coincidence? I don't think so. 6. The Sun's mass is about the mass of one cosmic scale atomic mass unit. In fission and explosions, the largest fission products are about 150 atomic mass units. Astronomers estimate the largest stars are about 150 solar masses. Another coincidence? I doubt it. 7th, after 11% of the Sun's hydrogen mass fuses into helium and an amount of iron equal to the cosmic scale electron's mass, the remaining hydrogen and helium is the mass of a cosmic scale proton. Another coincidence? Please. We can now use subquantum scale fusion to help us calculate the masses of all nuclei. Iron 56 is one of the most energetically stable nuclei. Starting with 56 separate nucleons, 30 neutrons, and 26 protons, from a total mass composition of 95% subquantum scale hydrogen and 5% subquantum scale helium. We must fuse all material into subquantum scale iron 56 in order to reproduce the mass of the iron 56 nucleus. The iron 56 nucleus is the most energetically stable nucleus precisely because it is composed entirely of sub-quantum scale iron-56 atoms. There's nothing left to fuse. This is the most amazing coincidence I have ever seen in my life. I was frightened by reality when I first calculated this back in 2007. Why do I believe our solar system was a cosmic scale neutron and is now cosmic scale beta decaying? In addition to these 7 reasons, during the past 28 years, I have never come across a measured physics phenomenon that I have not been able to reasonably describe within the fractal physics paradigm. I have always lived in the fractal universe. I'm inviting all of you to join me here. Again, I ask, will someone out there please build us a quantum scale camera to image neutrino energy? This Scalativity episode was produced by Z23 Studios. Make sure you subscribe to our Scalativity channel so you don't miss an episode. Please go to Scalativity.com to read the 5 initial fractal physics articles published online in the Fundamental Journal of Modern Physics. Scalativity.com also includes 3 groundbreaking, amazing articles available nowhere else. Until the next Scalativity episode, this is Leonard Malinowski, inviting you to help me advance physics.